Hello. So, in this second lecture on fluid kinematics, we are going to talk about rotation, angular deformation as well as linear deformation of a fluid element. So, in the previous lecture we discussed about that when a fluid element or when a fluid particle undergoes a motion, its motion can be decomposed into the four components, and those four components were translation. So, the translation refers to the motion of the particle from one location to another without actually any change in the shape of the fluid element. So, that is pure translation. Okay. In such a case, the distance between the corners of this rectangular fluid element does not change and its shape remains same. The second type of motion that we discussed was rotational motion. So, again the shape of the fluid element does not change, but it just rotates about a axis normal to the fluid element here. So, that is pure rotation. Now, the third motion of the fluid element we discussed is angular deformation. So, in case of angular deformation, the size of the fluid particles, if the fluid is incompressible, does not change, the size still remains same, but the angle changes. So, the angular deformation refers to the change in the angle between these two sides from 90 degree. The change that happens from 90 degree is what we will refer to angular deformation. And the last one is linear deformation. So, in the linear deformation we see that the size, it may get stretched or it may get compressed the side of the element. So, all those motions can occur simultaneously or generally occur simultaneously. What we did in the last lecture was looking at the translational motion of the fluid particle, and we derived an expression for the acceleration of the fluid particle for a known velocity field. We talked about the Eulerian and Lagrangian description, and because the velocity field is given in the Eulerian framework, we derived the expression for the acceleration or what is called substantial derivative for a fluid particle. In this lecture, what we are going to do is we are going to look at the rotation and angular deformation of the fluid particle first, and then we will talk briefly about linear deformation of this fluid element. So, let us consider a fluid element which is rectangular. Even though it appears to be square, we will assume it to be rectangular. The side AB is of a length delta x and side AD is of length delta y. The velocity components in the x, y and z direction at point A are u, v and w, and this is a two dimensional fluid element in x, y plane. Okay. It is named as the corners of the fluid element are named as A, B, C and D. This is at time t. At time t plus delta t, this fluid element undergoes rotation as well as angular deformation, and it deforms the corners A, B, C and D move to locations A star, B star, C star and D star respectively. So, that happens at time t plus delta t, and as we can see that the distance in y direction or the distance that point B has travelled with respect to point A in the y direction is delta eta. Similarly, the distance that point D has travelled in the x direction with respect to point A is delta psi, okay, and the angles that each side make from their previous locations, the side A star B star, it has rotated by an angle delta alpha, and side AD star, it has rotated by an angle delta beta, but in the different direction. So, delta alpha rotation, the rotation of side A star B star is in the rotation of side A star B star is in anti-clockwise direction, whereas rotation of side A star D star is in the clockwise direction by an amount delta beta. And we can see that this fluid element has gone rotation as well as angular deformation. So, what we are going to look at, try to decompose this motion of the fluid particle in rotation as well as angular deformation. So, let us see, if we assume that the pure rotation of fluid element or rotational component, it has rotated, let us say, by an angle delta theta, and if there would have been only rotation, then these the points of the particle would have been on the location A dash, B dash, C dash and D dash. Okay. Now, if it had been only angular deformation, then the angle would have changed by a magnitude of 2 gamma delta. So, gamma delta is the rotation of side A B, and gamma delta in the other direction is the rotation of side A D. So, the angular deformation of this fluid element is 2 gamma delta. So, sorry, 2 delta gamma. Okay. So, these are the two deformations of this element. Now, the total sum of, or the combined motion which causes the change delta alpha and delta beta. So, we can write delta alpha and delta beta in terms of delta theta and delta gamma. So, we see that the rotation of line AB, which changes from previous location, this dotted line, it has undergone, or it has rotated by a magnitude delta alpha in the anti-clockwise direction. So, this delta alpha will be equal to delta gamma plus delta theta, and in both of these cases the line AB is being rotated by an angle delta theta and delta gamma in the anti-clockwise direction. So, delta alpha is equal to delta gamma plus delta theta. Now, if we look at the rotation of line AD, then the net rotation is delta beta, which is in the clockwise direction, and this is being caused by a rotation of delta theta in anti-clockwise direction, and angular deformation or rotation of side A D by an amount delta gamma in the clockwise direction. So, delta beta will be equal to delta gamma minus delta theta. Note that this is in the anti-clockwise direction, whereas other two rotations are in the clockwise direction. So, that is why we have delta beta is equal to delta gamma minus delta theta. Now, our goal is to relate these angular movement delta alpha and delta beta, or thereby delta gamma and delta theta, because having known delta alpha and delta beta, we can solve these two equations and find delta gamma and delta theta. So, we need to relate it with the velocity of the fluid or the velocity field of the fluid. Now, as we said earlier that let us assume that the velocity of the fluid at point A is u v w, and what we need to see is that what is the movement or what is the displacement of the fluid element, or what is the displacement of point V from its previous position or with respect to point A. Okay. Similarly, we also need to see what is the movement of point D with respect to point A. So, for point B, the movement of point B with respect to point A is in y direction. Okay. So, we will need to consider the y component of velocity for point B and point A. So, we know that the y component of velocity at point A is v. By Taylor series, we can write that the y component of velocity at point B will be v plus delta v by delta x, that is the change in velocities delta v by delta x multiplied by the distance delta x. So, that is the velocity of point B. So, in time delta t, this position was at time t and the movement is after time t plus delta t. So, we can find out that what is the net displacement of point B with respect to point A in time delta t. Similarly, for point D, the velocity, because the point D moves in the x direction. So, we will consider the velocity component in the x direction at point D, and that will be from Taylor series expansion u plus del u by del y into delta y. Okay. So, now we can use these velocity components and try to relate the velocities with the net displacement delta eta and delta psi. So, delta eta is the difference between the distance travelled in time delta t by point B star or by point B and point A. So, the distance travelled in the y direction by point B will be v plus delta v by delta x into delta x multiplied by delta t minus the distance travelled by point A in time delta t, which will be v delta t, and we can see that v delta t will cancel out, and what we will have is dou v by dou x into delta x by delta multiplied by delta t. So, that is delta eta. Similarly, we can write an expression for delta psi, which is the displacement or of point D with respect to point A in time delta t along the x direction. So, the distance travelled by point D in time delta t will be its velocity at point D multiplied by time delta t, and the velocity is u plus dou u by dou y into delta y minus the distance travelled by point A in time delta t along x direction. So, that will be u delta t. So, we can again cancel out u delta t terms. So, we get delta psi is equal to dou u by dou y delta y into delta t. Now, we have obtained delta eta and delta psi in terms of partial derivatives of velocity components. Now, we can relate what we need to find is delta alpha and delta beta, because once we find that, we can find delta theta and delta gamma, which is the rotation of the fluid element and the angular deformation of the fluid element. So, now we can write that delta alpha is equal to delta eta over delta x, because if the delta alpha is small, then in that limit we can write that sine of delta alpha will be equal to delta alpha, and that will be equal to delta eta by delta x, the length of AB. So, delta eta by delta x, and from this expression we can substitute that delta eta by delta x will be dou v by dou x into delta t. Similarly, we can write that delta beta will be equal to delta psi divided by delta y, and from this we can obtain that delta psi over delta y is equal to dou u by dou y into delta t. So, we have obtained delta alpha and delta beta in terms of the velocity gradient and time delta t, or we can obtain delta alpha over delta t and delta beta over delta t. They are equal to dou v by dou x and dou u by dou y respectively. Okay. Now, our goal is to find delta theta and delta gamma. So, let us substitute those. We had these relationships, delta alpha is equal to delta gamma plus delta theta, and delta beta is equal to delta gamma minus delta theta. If we add these two equations, let us say these are equations 1 and 2, then we will get 2 delta gamma is equal to delta alpha plus delta beta, or delta gamma is equal to delta alpha plus delta beta by 2, and similarly delta theta is equal to delta alpha minus delta beta by 2. So, we can substitute the values of delta alpha and delta beta as we have found just now in terms of dou u by dou x and dou u or dou v by dou y. So, we can substitute those values. So, first we substitute, or first we find delta theta, where delta theta is the rotation of the fluid element. Okay. So, delta theta is equal to delta alpha minus delta beta by 2, and we can substitute these two values of delta alpha and delta beta in here. So, we get, when we substitute for delta alpha, dou v by dou x into delta t minus delta beta is equal to dou u by dou y into delta t. So, we get this expression for delta theta, or in the limit we can bring delta t here. So, we get delta theta over delta t is equal to dou v by dou x minus dou u by dou y divided by 2. So, delta theta by delta t, that is angular displacement per unit time, which is nothing but angular velocity. So, the rotation is in the z direction, or the vector will be pointing out in the z direction. So, z component of angular velocity will be equal to omega z is equal to half of dou v by dou x minus dou u by dou y. So, we have obtained the angular velocity or the rotational velocity of the fluid element. Similarly, we can do the same exercise for the rotation in zx and yz plane, and obtain the other two components of velocity. Okay. So, we get omega x by similar exercise we can find omega x is equal to half of dou by dou y of w, which is z component of velocity, minus dou by dou z of v, and omega y is equal to half of dou u by dou z minus dou by dou x of w. And we can write this in the vector form. The angular velocity vector will be omega is equal to half of dou by dou y of w minus dou b by dou z I, unit vector along the x direction, plus dou u by dou z minus dou w by dou x j plus dou v by dou x minus dou u by dou y k. So, we can obtain the angular velocity vectors in from the partial derivatives of the velocity components. Now, if we look at this expression closely, we see that this is nothing but the expression in bracket is nothing but del cross v. So, angular velocity omega of a fluid element is half of del cross v, where v is the velocity vector. So, we can write this in the vector notation in terms of a matrix for a cross product, that del cross v is equal to matrix the first row I j k del by del x, del by del y, del by del z u v w, and when we simplify this matrix we will get the terms in this bracket. So, the angular velocity is simply in vector form, it is easy to remember, half of del cross v. Now, because this half term is there, so to eliminate this half term, a new quantity or new term is defined, what is called vorticity, which is twice of angular velocity, and that is called del cross v. So, del cross v is called vorticity, and the term vorticity comes from vortex. So, vortex, from that vorticity comes, but the vorticity is not necessarily related to that there is a circulating fluid, or there is a vortex, and that will cause the vorticity. The vorticity represents the rotation of the fluid element itself. So, if there is a fluid element and if it does not rotate during its motion, let us say if it keeps its position constant during this circular motion, then it may not be rotating. So, if del cross v is equal to 0, then the flow will be irrotational, and irrotational flow, as we will see later on, that irrotational flow is a important tool to understand or to study inviscid flow, because the mathematics involved simplifies, and there has been lot of development in the expressions for irrotational flows. Now, irrotational flow, as we saw, that can happen when the fluid element rotates. And what can cause the fluid element to rotate? The fluid element can rotate because of two reasons. One, if it is rotating initially, then the fluid element may keep rotating, and the it will be rotating fluid, or it will have rotation, or if there is viscosity, because the other forces such as pressure force or the normal stress will not be able to cause the rotational motion, or the body force will not be able to cause rotation. So, the rotational force comes only from the shear stress, and as we saw earlier in the definition of viscosity or in the definition of fluid, that the shear stress in a fluid is caused because of viscous property of the fluid. So, only for the viscous fluids we can have rotational motion. So, for an inviscid fluid, the motion can be, or the flow can be irrotational. So, until now we have discussed what is delta theta. Now, we need to find delta gamma, which is the angular deformation of the fluid element. So, if we go back to our previous picture and look at the only angular deformation of the fluid element. So, this fluid element has gone a angular deformation of 2 delta gamma, that is change in angle between line AB and AD from 90 degree. So, that is 2 delta gamma. Now, delta gamma we obtained is delta alpha plus delta beta divided by 2. So, we can substitute the expressions that we derived for delta alpha and delta beta in terms of partial derivatives of velocity components u and v. So, when we substitute, we get delta gamma is equal to dou v by dou x plus dou u by dou y into delta t divided by 2, or delta gamma over delta t is dou v by dou x plus dou u by dou y divided by 2. But we know that the angular deformation is 2 delta gamma. So, that is why we have written here that the angular deformation or the rate of angular deformation of the fluid element in the xy plane gamma dot xy is equal to 2 delta gamma, which is the angular deformation, divided by delta t in the limit delta t tending to 0. So, that will be equal to del v by del x plus del u by del y. Similarly, we can obtain the angular deformation in the yz and zx plane. So, gamma dot or the rate of angular deformation in the yz plane, that will be equal to dou w by dou y plus dou v by dou z, and gamma dot zx is equal to dou u by dou z plus dou w by dou x. Now, this is what the components of strain rate or shear rate or rate of angular deformation are in xy, yz and zx plane, and these we can use when we derive the momentum equations and obtain the expressions for shear stress. So, for a Newtonian fluid, the generalized form of stresses can be written tau xy is equal to mu gamma dot xy, which is equal to mu dou v by dou x plus dou u by dou y. Similarly, tau yz is equal to mu gamma dot yz is equal to mu dou w by dou y plus dou v by dou z. And the third component or in zx plane, tau zx is equal to mu gamma dot zx is equal to mu dou u by dou z plus dou w by dou x. So, we can write the shear stress in terms of strain rates in a 3-dimensional flow for a Newtonian fluid. Okay. So, now we have obtained the rate of rotation or rotational velocity, or what we called in terms of vorticity, and the rate of angular deformation or strain rate or shear rate for a fluid element. Now, we need to look at the linear deformation of the fluid element. So, if we look at, let us say, if we see the fluid element at time t, and let us say if it has gone some linear deformation at time t plus delta t, then we can see the shape of the fluid element remains rectangle. So, the angle between AB and AD sides is still 90 degree. However, the length of the side AB has increased. So, the linear deformation, in the linear deformation what we will be looking at the strain or the change in the length of side AB. So, that we can find that how much point B has moved with respect to point A. Okay. So, the u component of velocity of point B, because we are now concerned in the motion of point V along the x direction. So, u component of velocity of point V will be u plus del u by dou u by dou x into delta x, that is the velocity u component of velocity at point B. So, the longitudinal rate of strain or rate of strain in x direction is the distance moved. So, the strain is the change in length of side AB. The change in length of side AB is the distance moved by point B. The distance moved by point B in time delta t will be time delta t multiplied by the velocity of point B, which is u plus dou u by dou x into delta x minus the distance moved by point A in time delta t, that will be u delta t. So, we can see that u delta t will cancel out, and this divided by delta x, which is the initial length of line AB. So, we will get strain, and as we will see that dou u by dou x into dou t into delta t will be the strain. When we divide it by delta t, we will get the rate of strain. So, the rate of strain in the x direction will be dou u by dou x. Similarly, we can find longitudinal rate of strain in the y direction will be dou v by dou y, and the longitudinal rate of strain in the z direction dou w by dou z. So, that is the rate of change of the sides of this fluid element in the x direction, dou u by dou x, dou u v by dou y, and dou w by dou z. Now, that will cause the change in the length of the sides will cause a total change in the volume, and that change in volume is what is called dilation. So, we can show from simple calculus that the change in volume will be sum of the change in the sides. So, that will be dou u by dou x plus dou v by dou y plus dou w by dou z into delta t, that will be the dilation in time delta t, or if we write in terms of rate, then volume dilation rate will be dou u by dou x plus dou v by dou y plus dou w by dou z, or if we look at this equation closely, we can identify that this is nothing but dot product of operator del and v. So, del dot v is the volume dilation rate, and as we will see when we see the continuity equation, that del dot v is equal to 0 is the condition for the flow to be incompressible. So, that means that del dot v is equal to 0, that means that the flow in the fluid the fluid particles do not stretch or do not get compressed. That means they do not get their volume they do not dilate, and that simply means that the flow is incompressible. Okay. So, we will stop here, but before we do that, I would like to extend my thanks to Dr. Amit Kumar, a colleague in the Department of Chemical Engineering, who has helped in the preparation of these slides. So, we teach the course at IIT Guwahati together. So, his help in preparation of these slides is gratefully acknowledged. Thank you.